Hello, wonderful people. Here we are, still in Chapter 8, Energy. This is Section 8.8, where we talk about mechanical advantage. Um, so that we're going to review a bit. In 8.7, we talked about lever, like down there in the picture. Archimedes. Have you ever heard of that name? He was a Greek philosopher who lived 2,200 and some years ago. He had a famous quote. He was the first person to think about what a lever does and put it in scientific terms. And once he realized the power of a lever, he said, "Give me a lever long enough and a place to put it, and I will move the world." And that's entirely true. There are some objectives for today's lesson, if you care about those kinds of things. And let's start with some review. So, what is a machine? Machines make work easier by doing one of three things. They change the force that you exert. So if you input a certain amount of force, you get a different force as an output. It can also change the distance that the force works. So when I'm raking leaves, I move my hand back and forth just a foot, but the rake moves, 3, 4, 5 feet across the ground. And finally, the third one, changing the direction the force is exerted. And that's like the pulley there over in the picture on the right. So let's talk about that pulley picture for a minute. Can I draw in, if I've got between there and there, so between those two red lines, they're about a foot apart, right? In the picture. So that means that there's 1 foot of rope there and 1 foot of rope over there. So if this guy wants to pull on this system and lift this load up 1 foot, he's got to take out these 2 feet of rope. Does that make sense? So that means that he's got to move from there to there. That's how far he has to move, has to pull the rope. He has to pull this 2 feet of rope out in order for these 2 feet of rope to go away, and the load lifts up 1 foot. Now, if that didn't make good sense, please go back and listen to that again and figure this example out. Because if you have that in your head and you understand how this guy pulls on 2 feet, it goes up 1 foot, that will make the rest of this a whole lot easier. Because then we take this 2 and 1 and we turn it into a ratio, and that's pretty much what this whole section is about, because that ratio tells us, that's the where mechanical advantage, that is showing us mechanical advantage is that ratio. So let's set this up. Which is easier, opening a paint can with your fingers or opening a paint can with a screwdriver? Have you ever tried to open a paint can with your fingers? It's very hard. I tapped a lid just a little bit shut just to keep it from drying out. And I looked down at the paint can and I'm like, oh, that lid is still pretty much off. So I reached in there with my fingers and I tried to pop it off, and it just hurt a lot. And I kept trying because the screwdriver was on the other side of the room. So we all know the answer to this. Opening a paint can with a screwdriver is much easier. And if you look at the picture, the lever, that's acting as a lever. You're pushing down here. The fulcrum is the edge of the paint can, and then the very tip goes up and pries the can off. And the paint can, the lid represents the red energy of the friction pushing down. So that's the load that you're working against to pop the can off. Let's do another example. Which is easier, lifting a box into a heavy truck or pushing a heavy box up a ramp into a truck? If you've ever done this, and I'm sure most people have, you've had something just too heavy, so you just push it up the ramp or up the stairs rather than trying to carry it. Yeah, that's an easy one. So when you're using a machine to do work, there are two forces that are involved. The first is the input force. That's the force that I apply to the machine that that I apply to the machine. And then the output force is the force that the machine applies to the object that we're trying to do the work on. Two types of work are involved. So there's the input work and the output work. Please note that work is different than force. So in this, we were talking about the input force. Now we're talking about the input work. And what's the relationship between work and force? Remember, work equals force times distance. So the work input on the machine, the work done on the machine, is the input force times the input distance, how far that force moves. And then the work output is the same idea, the output force times the distance that it moves in doing that work. So how are the two related? Let's do some examples. Okay. We're going to skip that slide and just go to the example of there's the wheelbarrow. So in the wheelbarrow is a load of, say, 300 pounds, which is too heavy for me to lift. So if I lift up on the handles of the wheelbarrow, and in a real wheelbarrow, the handles are further away than this usually, I lift up about a foot and a half to get the wheelbarrow off the ground. So I'm lifting up a foot. And then where'd my arrow go? The wheelbarrow lifts just a couple inches up off the ground. So I'm applying 100-pound force through about a foot of distance. So that's my work is 100 pounds times the distance 1 foot. Then the wheelbarrow, because it's acting like a lever, I've got a force out here. The wheelbarrow lifting the load of the 300 pounds of brick in there, it only has to lift it a few inches. And so that's how it does it. It's able to lift, it takes the small force that I input and outputs a larger force, but it's going across a shorter distance. Does that make sense? Here's another great example, the classic hammer. So you see the little red line there? That shows how much my wrist is moving. I'm just flicking my wrist back and forth to swing the hammer. So I'm moving my wrist is moving a short distance, but the hammer head is moving a large distance. So now I'm inputting a force over a short distance, and a smaller force is being applied over a long distance. Because I'm not worried about how hard the hammer hits, I just want it to have a good velocity. All right, so now we get into the benefits, measuring the benefits of mechanical advantage. So how do we measure this and put some numbers to it? So mechanical advantage tells you how many times the machine multiplies the force. Please note, mechanical advantage is talking about the force involved. So a machine with a large mechanical advantage can make lifting a heavy load easier, like the wheelbarrow. And there's the equation. Mechanical advantage, actual mechanical advantage is the force out divided by the force in. And then ideal over there is ideal mechanical advantage, and that's where you ignore friction. So that's good enough for that. We don't need to go into too much more details about that. So how do you calculate mechanical advantage? And this is what the homework entails. So if I tell you that a machine has a mechanical advantage, I misphrased it. Number one, what is the mechanical advantage of a machine that applies 200 newtons to an object when you apply 50 newtons to the machine? So there's our equation for mechanical advantage. The force out divided by the force in. So How do I solve for mechanical advantage? I just plug in 200 newtons, the force out, divided by 50 newtons, the force in, and I solve for that, and I get an answer of 4. Please note that the newtons divided by newtons cancels the units. So this hardly ever happens in physics, but right there we have a number with no units. So that's a little different than what we're used to. So there's problem number 1. Let's try another. You apply 2,000 newtons to a machine, and the machine applies 200 newtons to an object. What is the mechanical advantage? So once again, there's our mechanical advantage equation. The force out is 200 newtons. The force in is 2,000 newtons. So in this case, the mechanical advantage is 0.1. Please note that is less than 1. And then finally, for the third problem, you apply 10 newtons to a machine and the machine applies 10 newtons to another object. What is the mechanical advantage? Now, before we answer that, can you think of an example of an actual machine where you apply a force and you get the same force coming out of the machine? The pulley is a great example. So if I want to lift a load up and I have a pulley up in the ceiling, when I pull down on the rope, if I pull down with 10 newtons, the pulley pulls up with 10 newtons. And all that machine is doing is changing the direction of the force. That's the trick of what a pulley does. So yes, there are plenty of times, 99% of the time it will be with a pulley, where where the machine has a mechanical advantage of 1. 10 newtons in divided by 10 newtons, 10 newtons out divided by 10 newtons in gives 1. So let's go on to the next slide. Can such a machine be useful? So here we go. What does it mean? If a mechanical advantage is 1, then there is no advantage to using the machine. And this is where things get weird. Because when that sentence says there is no advantage to using the machine, that's talking about mechanical advantage. And that is a scientific term. We defined it. Force out over force in. So please don't get hung up on the English definition of advantage. That's not to say there is no purpose to using the machine. There is no reason to using the machine. No, there's plenty of reasons to use a pulley or any machine that has a mechanical advantage of 1. That sentence is just saying that that machine has no mechanical advantage as defined by that formula. So this is an excellent example of why I say science is just like a foreign language, because we put technical definitions to these words, and then you have to learn that technical definition. We all know the word advantage. That's used in everyday life, but that's everyday definition is not what we're talking about in this situation. Are you with me there? Good. So then if mechanical advantage is greater than 1, the machine makes work easier, and if the mechanical advantage is less than 1, the machine makes work harder. This is all just talking about mechanical advantage. Then we come to efficiency. And the very last line, no machine has 100% efficiency due to friction. We've talked about friction and that kind of stuff before. So let's just calculate efficiency. So now we're talking about work, and we measure work with joules. So if I put 40 joules of work into a machine and it puts 30 joules out, how efficient is the machine? There's our equation, work out divided by work in, and then convert it to a percentage. So in this case, 30 divided by 40, changed to a percentage, is 75%. And what does this tell us? That anytime I put work into this machine, whatever work I put in, I'm going to get 75% of that coming out of the machine as useful work. Where does the rest go? It just gets used up by the machine. Friction, heat, sound, vibration, all the usual places where friction goes and dissipates as heat. Okay, so have you ever seen one of those hand mowers there in the picture? Let's say that you spend some time cutting your grass and you do 250,000 joules of work to cut the lawn with that hand mower. Now the work done by the mower is 200,000 joules. So what is the efficiency of that lawnmower? There's our equation, work out divided by work in, and 200,000 divided by 250,000, the units cancel, convert it to a percentage, 80%. Does that seem pretty straightforward? Oh, and that's the end of that. So I'm going to ask you to go try the 2 or 3 homework problems there are. And if you have any troubles, please just ask a question. Thank you so much.